Today we're going to create a function for differentiating unequally spaced data, and we're just going to start off with 3 data points. We'll create the Lagrange polynomial that would go through those 3 points. This is from our interpolation section. And now note, the only thing that actually has x's in it are the numerators, right? The things that you see in the denominator are x1, x2, x3. Those are just the points from our data set. So the only actual x's are in the numerators. So I'm going to distribute in the numerators, and we'll end up with this right here. And then lastly, differentiating, you can see if you take the derivative of x squared, we get 2x. The derivative of minus x3 times x would be minus x3, and the derivative of x2 times x would just be x2, and then finally the derivative of the constant term would be 0. Okay. And we just did that for all 3 of these, all 3 of those terms. And so we'll use this right here to approximate our derivative at points that are, between x1 and x3. Okay. Let's go ahead and switch over to Matlab. And let's get our function started here. So we're going to start our function with the word function, as always. And the output, let's make that capital D lowercase f for the derivative of f. And let's name this function deriv uneq. And so all we really mean here is that we're taking the derivative of unequally spaced data. When we use this function, we're going to need our 2 data sets. So how about x and y? Okay, and let's start typing in that formula that we have highlighted down here. Okay, that's what df is going to be equal to. Okay, we might make some adjustments to what we're going to do here in a little bit, but let's just get started by getting that all in here. Okay. And one more thing, let's also put an input here. So we want to take the derivative at a specific point. Let's say that that point is xx. Okay. Now that we have our first term typed in, okay, you can see I've just replaced the x's in the formula with xx, and the x sub 3 and x sub 2 are now just x of 3 and x of 2. Okay. But this is going to end up being such a long formula that I put dot 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 here. So remember, we can then continue on to the next line here. We could then say plus 2 times xx, and we'll type in the rest of this. Okay, and here are our last 2 terms. So this could be it. Okay. But what if we have a larger data set? Then what do we do? Well, if we have more than 3 points, is what we could do is we could just see, well, what points in our data set are close to xx, and we'll use those to perform the Lagrange interpolation. Okay. Or in other words, use this formula on the points that are close to xx. Okay. So let's get that going here. Okay. So if we wanted to do that, we would want to start by just figuring out, well, what are the length of these vectors? So that'd be a good start. And of course we need these to be the same length. So we could put in a couple things to catch some errors here. So how about if the length of x, which is n, is not equal to the length of y, then we have a problem. Error. X and y should be the same length. Okay. But another issue can arise. We're going to need x and y to be column vectors for this. Okay. So the trick here is we need to find the size of both of these. So let's maybe say size of x, size of y, and let's maybe let the first element here be r1 for the number of rows for x, or maybe rx. How about that? Okay. And then cx for the number of columns in x. And we'll do the same thing here for y, ry and cy. Okay. And so what we're going to want to do with these is if the number of columns is more than 1 for either one of these, we have an issue. So if cx is greater than 1, okay, or cy is greater than 1, what do we want to do? We want an error. Okay. X and y must be column vectors. Okay. And we'll go ahead and we'll end that. Alright, now we haven't done a whole lot other than just getting this formula in here and then catching whether we've input anything wrong here. Okay. But we could do a little more. We could in fact actually add one more thing here. If nargan, okay, is less than 3, we have an issue, right? We need 3 input arguments here. So if nargan is less than 3, we'll also report an error. 3 input arguments required. Or how about just 3 inputs required? Okay. But now the question is, how are we actually going to deal with these x and y vectors if they're bigger than 3? Okay. Well, we just want to essentially use the points around xx that we choose here. Okay. So we can do that. We can look at how close xx is to some of these other points. Okay. So we could do xx times a vector of 1. So I'm going to say, this is why we need this to be a column vector here. 1s, and we're going to make this into a column vector, an n by 1. And we're going to subtract this from the x vector. So essentially is what we're doing here is we're seeing what's the difference between xx and all our x vectors. Okay. And is what I want us to do from there is then take the absolute value of that. Okay. And is what we'd really like to know is what's the minimum difference here. Okay. So we'll do that. We'll take the minimum of it. And let's set this equal to, how about min comma I. Okay. So I is going to be the location in the vector x that has the minimum distance between itself and xx. Okay. What we input there. Let's go ahead and suppress that. Okay. And is what we'd ideally like to do here is create some new vectors. Okay. Maybe we'll call them big X and big Y. Okay. And these will be based on taking the little x's and going one to the left from the closest x to xx. Okay. And then in the middle, we'll actually be looking at the point closest to xx, and then we'll go 1 point to the right, so I plus 1. Okay. And we'll do the same thing for y here, y of I minus 1, y of I, and y of I plus 1. Now the only thing we're going to have to change here is we're going to just need to change these lowercase x's to uppercase, and same for these lowercase y's here. We'll have to change those to uppercase. That's an easy fix. Go through and do that real quick. Right, and it looks like just 2 more to change. Okay, there we go. It's all changed. Okay. And so again, is what our code's doing here is you're going to take some point that you'd like to find the derivative at, okay, and it's going to use this minimum function here, okay, to find the x that is closest to it, and then it's going to choose one to the left, one x value to the left and one to the right. And these are going to be the points that we're going to use that Lagrange interpolation for. Okay. And that's what will be used to estimate our derivative, okay, or just those points around it. But now the question is, well, what do we do if x of I is the left endpoint? Okay, so we need to build that in here. What do we do if we're at the ends? Okay, and so this is an easy fix. We can just say up here, I'm going to do this right here. If I is equal to 1, okay, so if I is 1, just make I equal to 2. Okay. And that would be for one end if we're on the far left. Okay. And this is just ensuring that we'll now use the first 3 points to create our quadratic that we end up differentiating here. And if we're at the other end, so else if, so if I is equal to n, okay, then we'd want to let I equal n minus 1. Okay. Let's go ahead and save this and go test it out. Okay. Let's test it out on some equally spaced data maybe here in a minute. Let's start off with x equals linspace from 0 to 2 pi. Okay. And the default is 100. So we're going to use 100 points. They're going to be pretty close. And they'll actually be equally spaced here. But we'll try this out on some unequally spaced data here in a bit. So next we have y is equal to, and let's just do sine of x. Okay. And from here we could actually plot this. We already know what it looks like, so I'm not going to have us look at it. And let's try to take the derivative at a bunch of points here. We're going to use that deriv unequal function. Okay. So deriv unequal. Okay. We need to put in our data here. And remember, we wanted these to be column vectors. And so we do x comma y here. And we'd like to evaluate this at a point. And let's turn this into a function. That way we can plot it. Actually, maybe I'll call this dy. Okay. So dy, our variable will be xx, and let's plot it, fplot. Okay. And we're going to go from 0 to 2 pi. Okay. And we'll see if we get any error messages. Okay. So I see sine of x here. I do not see our other plot. Let's see what went wrong here. let's make a few quick edits here. So I see that we made x into a column vector, but y we transposed as well, but it was already going to be a column vector because x was. So we can get rid of this extra transpose here. Let's get rid of that. Let's go over to our derive unequal function, and I can see here that I have a missing end here. And just so that we don't have any conflict between the min function and this min value, let's just call this m. Okay. Let's go ahead and hit save now that we've made those edits. Let's go back to this untitled 8 here, and let's go ahead and try and plot this function. I did make a couple of changes that I need to go back in here and make here again. So dy again was a function of xx, and I think that was the only other change we had made. Okay, let's go ahead and run it. Okay, there we go. And so what we have there in the red does look like cosine. So this function is behaving really well for equally spaced data. Let's test out what happens for unequally spaced data. Okay, we have us some data here, and let's see what it looks like. I want to first note that it is unequally spaced for those t values. But let's see what it looks like. Okay. So we'd have what, t comma v here, and let's just plot the points. Okay. And I just need to switch that to a capital V. Okay. And you could kind of see that this, it might be fit okay with maybe part of a quadratic, or maybe even a linear line here. Okay. Or maybe we could use splines to connect these since it's not super clear. Let's maybe try that. Okay. So let's try and do interp1. Okay. We'll go t comma v. We'll evaluate it at some point, and let's use the spline setting. And again, our variable here is going to be xx. Okay. And let's just call this v fun. Okay. And we'll hold on, and we're going to use fplot to plot v here. So v, and we are going to plot it over the interval from 0 to 75. Let's see how it looks. Okay, that does not look good, and I think I know why. It is because we are missing something here on V. We are missing V fun. There we go, and now it's interpolated perfectly. Now, let's see what kind of derivative we can get out of this. Okay. Because we could differentiate this function right here using the deriv f function we created the other day, but I'll want us to also compare a result to what we get by using this new function we created. Okay, let's go ahead and do that. Okay, so how about we call the next one here v prime 1. Okay. And is what we'd like to do is take the derivative, so deriv 1, sorry, not deriv 1, deriv f. Okay. Let's remind ourselves of what the inputs to that function looked like. It would be a function f, a point x, and then what we want to use for h. Okay. So we want first the function, so that'd be v fun. Okay. We would like to plug in a specific value. How about we also call that value, let's just call it x. That'll be fine. All right, at x here. And the only other thing we need to do is pick an h. And we just want to pick it to be something small. Okay. And let's go ahead and plot this as well. Okay. So let's do plot. And let's use fplot since we wrote this as a function. And then v prime. Okay. And let's plot it over the interval 0 to 75. Okay. Let's see what we got. Oh, and I'm missing the 1. V prime 1. Okay. All right, and so you can see our derivative function down here. Let's put these on 2 separate plots. Okay. Let's maybe do subplot here. And let's stack these. So maybe let's do 2 by 1 grid, and this will be the first location. And for this next one here, let's do subplot. And again, it's a 2 by 1 grid, but this will go in the second location. And is what we're going to eventually do here is we're going to put our 2 estimates for the derivative side by side here. Okay, but up here, this top graph, let's maybe just title it let's just title it voltage. Okay. And we'll title the next one here derivative of voltage. Okay, and I'm not seeing those titles, and I'm going to put them below the plots. I think that'll make those pop up. Okay, there's one. And let's move the other one below the plotting as well. Okay. There we go. We have our voltage, derivative of voltage. And now let's try out that trap unequal. And we're going to want to make sure we hold on here before we actually plot this other function. But let's call this new function here. Let's call it v prime 2. Okay. And let's think about what function we want to use. Well, we want to use this new one. Okay. So v prime 2 is going to be calculated using deriv unequal. Okay. And let's also choose our input maybe to be x here. Okay. And then we have our data t comma v. Okay. And right after v, it's just what point do you want to plug in? Okay. We want to plug in x. Okay. All right, and then from here we should be able to plot this. So let's say fplot. And I think we could just pretty much copy this right here, our other fplot. Okay. And we just need to change this to v prime 2. Okay, it looks like we got some error messages here again. And it looks like I've used a lowercase v. Let's fix that and make that an uppercase v. Okay. And here we go. We have both of our results. And you can see they actually pretty closely match because we're talking about really small numbers here. One thing I do want to say is the fact that we split or fit this with a spline, okay, or a bunch of splines, means that it does pick up the curvature here a little bit. Like, for instance, let's say we fit this with a quadratic, right? It wouldn't go through all these points, and it would be fairly smooth. It wouldn't pick up some of this subtle curvature here. Okay, so that's something you have to watch out for if you choose to perform regression instead of interpolation. All right, and that is it.